You ever stop and think about the buildings we're in every single day? I mean, really think about them? There are these incredible invisible forces at play, currents and pressures that almost make a skyscraper feel like it's a living, breathing thing.
And I'm sure you felt it. You walk into a lobby in the middle of winter and bam, you're hit with this blast of cold air. Or you go to pull open a big glass door and it feels like it's fighting you. It's so easy to just blame it on the wind, but that's not the whole story, not even close. There's something else going on, a really powerful force that the building is creating all by itself.
So, here's what we're going to do. We are going to pull back the curtain on this whole thing. We'll start with a mystery, then we'll break down the actual physics, look at what happens when it all goes wrong, and then, my favorite part, see how engineers and architects get really clever to design around it. All right, first things first. Let's put a name to this invisible force and figure out what it's all about. It's called the stack effect, and honestly, the other name for it, the chimney effect, is just perfect, because that's exactly what's happening. Tall buildings with all those elevator shafts and stairwells, they basically act like giant chimneys, creating this constant, surprisingly powerful flow of air. So, how does a skyscraper actually turn into a chimney? The physics are, believe it or not, pretty simple. But the effects, they are huge.
Okay, so what it really boils down to is one word, buoyancy. It's all driven by the difference in air density between the warm air inside and the air outside, and that usually comes down to temperature. We all know hot air is less dense, it wants to rise. Cold air is denser, so it wants to sink. That's it. That's the core principle.
And this is a perfect way to see it in action. On the left, you've got winter. The warm, cozy air inside is lighter, so it rises up through the building and escapes out the top. This creates a vacuum, a negative pressure at the bottom, that literally sucks cold air in. Now look at the right, summertime. The whole process flips. The cool, air-conditioned indoor air is now denser than the hot air outside, so it sinks, pushes out of the lower floors, and pulls hot air in from the top. It's the exact same physics, just running in reverse. Let's dig a little deeper now. How do these air movements build up into real, measurable forces? To get that, we need to talk about pressure, and a really crucial concept for understanding this whole process. And that concept is the neutral pressure plane, or NPL. The easiest way to think about this is as the building's balancing point. It's this one theoretical level, somewhere in the middle of the building, where the inside air pressure and the outside air pressure are exactly the same. There's no push, no pull. It's neutral. And everything that happens with the stack effect happens above or below this invisible line. And this diagram just lays it out perfectly. In winter, everything happening below that neutral pressure plane is what we call infiltration. Cold outside air is being sucked in. And everything above that line is exfiltration. Warm inside air is being pushed out. This simple idea, this dividing line, is the key to understanding all the problems and all the solutions that we're about to get into. So just how strong are we talking? Well, some research on a 20-story building found pressure differences as high as 70 to 80 pascals on those lower floors. Now that number might not mean much, but get this. That's about the same pressure as a steady wind blowing at almost 30 miles per hour. And remember, this isn't the wind outside. This is a force the building is creating all by itself, just from the temperature difference. It's pretty amazing. Okay, now check this out. This shows you just how much local climate can crank this effect up to 11. On the left, that's a building in Astana, Kazakhstan during a brutal winter. See how wide those bars are? That's a massive pressure difference. Now look at the right, a building in Riyadh, Saudi Arabia, in the summer. The reverse stack effect is happening, but see how much smaller the spread is? It's just less severe. This really hammers home why you can't have a one-size-fits-all design. Okay, we've got the physics down. But what happens in the real world when this powerful, invisible force isn't managed properly? What happens when a building's breath turns into a gale? The problems range from just plain annoying to seriously dangerous. You get those malfunctioning doors that are hard to open, those constant drafts, weird whistling noises from air screaming through tiny gaps. But then it gets much more serious. This uncontrolled airflow can spread smoke, smells, and contaminants all through a building. It makes your heating and cooling systems work way overtime, which means huge energy bills. And maybe worst of all, it can completely undermine a building's fire safety plan. And that point about fire safety, that is absolutely critical. Like this says, the stack effect can turn stairwells and elevator shafts into the perfect chimneys for fire and smoke. Tragically, investigations into major fires, like the Grenfell Tower fire, have shown how this very phenomenon can help a fire spread upwards with terrifying speed and devastating results. So you might be thinking, how on earth do you fight back against basic physics? Well, the good news is architects and engineers have a whole toolbox full of clever strategies to tame a building's breath and get it back under control. And it really is all about control. Revolving doors and vestibules, they're basically airlocks to prevent those huge gusts of air. Making the building's outer skin, its envelope, as airtight as possible is absolutely fundamental. Then, on the inside, you break up that giant chimney by compartmentalizing shafts and stairwells. And you can even use modern HVAC systems to fight fire with fire, so to speak, by strategically pressurizing certain areas to counteract the stack effect. You know, what this all really does is it forces you to see buildings in a completely new way. They aren't just these static, lifeless objects made of steel and glass. They're dynamic systems. They're constantly in this push and pull with the outside world, inhaling and exhaling with the changing seasons. So the next time you feel that draft or you have to lean into a heavy lobby door, you'll know what's really happening. It's not just the wind, it's the building itself taking a deep breath. It kind of makes you wonder, doesn't it? What other huge, invisible forces are out there shaping the world we've built all around us?